In today's video, we're going to be talking about riverboat problems. After watching this video, you should be able to understand what relative velocity is, and then be able to apply that to solve some problems that are typically called riverboat problems, but they're basically problems where the velocity perceived by an observer is different than the velocity of a person, say, on the object. So for instance, if we're watching a boat go down a river, the velocity for the people on the boat is going to be a little bit different than, say, someone who's standing on the shoreline. But we'll get into that in just a second. Let's start to take a look at some stuff. So relative velocity. On occasion, objects moved within a medium that is moving with respect to an observer. So like a river, for instance, or say a hang glider in the air. These types are an airplane, are types of things that move in a substance that also may be moving in itself. So like the water is moving or the air is moving or something like that. So for example, an airplane usually encounters some wind, air that is moving with respect to an observer on the ground. So if a plane is traveling at a velocity with 100 kilometers per hour with respect to the air, and if it has a tailwind velocity of 25 kilometers per hour, what is the velocity of the plane relative to an observer on the ground? Well, that's a good question. If we have, basically if we just start to draw our vector diagrams, we can just, it doesn't say so much in terms of a direction, so I'm just going to put down here, here's my plane vector, and it's going 100 kilometers per hour. And we have some wind, tailwind, going in the same direction, that's 25 kilometers per hour. So this is pretty basic. It's back to kind of what you guys were doing at the very beginning of this unit. If you add 100 plus 25, how fast does the plane appear to be to someone who's, like, say, standing on the ground looking up at the plane? Well, you just would make this into one big long vector, and it would be 125 kilometers per hour. This is the relative velocity. So someone on the plane is experiencing a velocity of 100 kilometers per hour, but if you were observing it from the ground, it appears to be going 125 kilometers per hour. Okay. So here is another example. This time it says a plane is traveling with a velocity of 100 kilometers per hour south. So I'm going to draw that in here. 100 kilometers per hour south, and encounters a side wind of 25 kilometers per hour west. So let me put that in here. 25 kilometers per hour west. What would the resulting velocity of the plane be? All right, so this is just basically adding vectors, right? Head to tail method, and let me just change pen colors here so I can make my resultant different. Here is the resultant vector right here. Okay, where I just connect from the tail of the first vector to the head of the second, or the last vector, I should say, and then we have our resultant, which I'll just label R. To figure out the resultant, basically I'm going to use the Pythagorean theorem, where I have 100 squared plus 25 squared equals R squared. And if you do that math, I get an R of 100, sorry, I'll make that look a little better, 103 kilometers per hour. So let's take a look at some riverboat problems. With the riverboat problems, basically the idea is that a boat is moving in a river, and you've got different vectors interacting with one another. So it says, suppose that a river was moving with a velocity of 3 meters per second north, and the motorboat was moving with a velocity of 4 meters per second east. What would the resultant velocity of the motorboat be relative to an observer on the shore? So let's start it off with, here is my boat. It is going 4 meters per second east, and then the river, if you can imagine a river here, is moving north at 3 meters per second. I am going to create the resultant vector in red this time, and so I just would connect it like so. And here's my R. I want to know, what is R? Well, basically, if I use the Pythagorean theorem, 4 squared plus 3 squared equals R squared, I would get an R of 5 meters per second. Okay, so that would be the resultant velocity of this motorboat to an observer on the shore. Now remember, velocity should have a direction to it. So east is like right here along this line. Okay, this would be my east line. How many degrees is this angle right here? How many degrees is that angle? So to figure that out, I would just take the tangent of theta equals opposite, which is 3, over adjacent, which is 4, 3 over 4. I have to take the inverse tangent, so it'd be inverse tangent 3 over 4. And if you do that math problem, I get about, I'll round up, about 37 degrees, okay, from east. Okay, so about 37 degrees from east. So that's an example of one type of riverboat problem. Now we're going to make it maybe a little bit more challenging here because we're going to kind of discuss what typical riverboat problems ask. Usually it's 3 questions. What is the resultant velocity? So both the magnitude and direction of the boat, which we just did in the previous slide. We calculated the resultant velocity of the boat. The 2 questions we didn't answer in the previous question was, if they tell you the width of the river in some amount of width, either meters, feet, whatever, how long would it take the boat to travel from shore to shore? That's a very typical question that you probably will see, is how long would it take the boat to go from starting at one side of the shore to the other? And then another question that typically is asked is, what distance downstream does the boat reach opposite the shore? So I mean, like if a boat just goes straight across a river and the river is running into it, clearly the boat can't just make a straight line across the river. It's going to have to, or it's going to move downstream a little bit because the water carries it that way. The question is, what distance downstream does the boat reach? Okay, and I'm going to do 2 examples with this to kind of give you an idea on how these problems would work. So here we go. Let me just change pen colors here so you can actually see it. Let's do green. So it says a motorboat is traveling 4 meters per second east, 4 meters per second east, and it encounters a current traveling 3 meters per second north. Let me change colors for the resultant. So the resultant would be right here. And we actually just did this problem. These are the same exact numbers. So the resultant is 5 meters per second at about 37 degrees. Okay, so we just did the first one, and we did that in the previous slide. Now here are the 2 other questions I mentioned that are very typical with riverboat problems. If the width of the river is 80 meters wide, so let me just draw a little river here, and like here's some water. Okay. If the width of this river, so from here to there, is 80 meters, okay, how much time does it take the boat to travel from shore to shore? This is where students get a little bit confused. It's not that it's the math itself is so difficult, but really you have 3 velocities here, right? You have, this is the velocity of the boat. This is the velocity of the river. So I'm writing v boat, v river. And this is the resultant velocity. This is the result of the velocity of the river and the boat put together. Which of these 3 do you use? Oh, I'm sorry, the resultant is this 5 meters per second. Sorry, that's not so clear. Now maybe a little more clear. Which of these do you use? Well, I don't know if you remember, a while back in one of the lessons many, many moons ago, we talked about that vectors that are perpendicular to one another have no role or do not affect one another. So this vector here that's traveling east compared to the vector that's going north, they are perpendicular to each other, perfectly perpendicular, and so they do not influence one another. So when we're looking at the 80 meters, that's basically looking at the eastern vector, the 4 meters per second, and that is the velocity I want to use. I want to use the 4 meters per second. How long would it take a boat to travel 80 meters? Well, that's just basically a good old-fashioned like speed question, right? Where like this is a formula you may have learned in middle school. Speed equals distance over time. Well, we know the speed, which is velocity in this case, and we know the distance, right? We just don't know time. That's what they're asking is how long would it take to travel 80 meters? So if I just rework this equation, time equals distance divided by speed. So the distance is 80 meters, and the speed is 4 meters per second. So 80 divided by 4 would be 20 seconds. That's how long it would take the boat to cross the river. It would be 20 seconds, okay? Now, let me change pen colors here so that maybe this becomes a little bit more clear. The third question is, what distance downstream does the boat reach up on the opposite side of the shore? Okay, so as this boat kind of like travels across this river, it's not going to be able to go in a straight line. Instead, it's going to go something like this. Okay, so the yellow dots are the path. The question is, what is this distance right here? Okay, how far off was it as it moved? Okay, now remember, vectors that are perpendicular to each other really do not interact with one another. So we have three velocities here, right? We have the resultant velocity, we have the boat velocity, and we have the velocity of the river. Who is going to be in charge for moving, or which of those velocities would be in charge for moving this boat downstream? To move the boat downstream. So kind of think about that. Well, that's going to be the velocity of the river. So we're going to be using this number here, 3 meters per second. So I'm going to be using this formula right here. I'm just going to manipulate it to basically say distance, which I'll represent with a d, equals speed times time. Okay. Well, how long did it take the boat to get across the river? 20 seconds. We just solved that right here. So I know the time, which is 20 seconds, and I know the speed, which is 3 meters per second. So if you take 3 times 20, the distance would be 60 meters downstream. So that distance there would be 60 meters. Okay. So I think you guys can see now the math itself isn't out of this world hard. It's more of using your brain and understanding how vectors work, and how that you have to look at individual components of the vectors and figure out which one to use in the problems. Because if you use the wrong velocity, then your answers are not correct. Okay. If you're still concerned, don't worry. I have another problem coming right up. Let me change pen colors here. Do some red. Okay, it says a boat traveling 4 meters per second east. Okay, traveling 4 meters per second east encounters a current traveling 7 meters per second north. Okay, what is the resultant velocity of the boat? All right, let's do that first. We'll do blue. So the resultant velocity is going to be this guy right here. I'll try to make this nice and bold because the blue doesn't come out real well against black. The resultant velocity is going to be right there. So I'm going to be using the Pythagorean theorem to figure out r. Okay, so I'm going to take 4 squared plus 7 squared equals r squared. And if you do that math, you should get an r of 8.06 meters per second. Now that's just the magnitude. What about the direction? What about theta here? Okay, to get theta, I'm going to take the tangent of theta equals opposite, which is 7, over adjacent, which is 4. Take the inverse of this, so tangent theta negative 1, 7 over 4. And if you do that math, you should get a theta of 60.3 degrees. Okay, so that answers this problem here. What is the resultant velocity of the motorboat? Okay, it would be 8.06 meters per second. I'll write that in over here. And it's at an angle of 60.3 degrees from east, or due east. Okay. Now it says, if the width of the river is 80 meters wide, how long would it take for the boat to travel shore to shore? Okay, so here's the river. And again, you guys can see some of my phenomenal artwork. There's the river. And this is 80 meters going straight across. Okay. How long would it take to travel shore to shore? Okay, let me change pen colors so we can stay on this piece. So again, you have 3 velocities here, right? You have the velocity of the boat, you have the velocity of the river, and here is the resultant, which is the velocity of the boat and the river put together. Okay. Which of these numbers would be useful for calculating how long it would take to go from here to there, basically directly east? Hopefully you're thinking this one right here, the 4 meters per second, the velocity of the boat. Okay, they want to know how long would it take. Okay, so I'm going to use the formula time equals distance over speed. Okay, so I want to know time. Do I know distance? I do. They tell me it's 80 meters. Do I know speed? I do. They told me the boat's going 4 meters per second. And so this would take 20 seconds. And you may say, hey, that's the same number as last time. This is true. The reason I'm doing this example is to make a point that the speed of the river actually has nothing to do with how long it takes the boat to go directly due east. The only vector component that's important to worry about is the boat's speed, okay? So again, the river could be going, 20 meters per second. It still would take the boat 20 seconds to cross the river at 4 meters per second. The only thing that's going to affect that is if this number gets bigger, the 4 meters per second. If we could crank the boat up to 8 meters per second, then absolutely it would go faster. It would take half the time, actually, okay? But this is to make a point that these vectors are completely independent of one another, okay? So we've answered that question. Let's answer the last one, and one more pen color. I'm feeling like magenta. I think that'll be fun. What distance down the stream does the boat reach opposite the shore? So basically, we know that this boat is traveling at some angle, and actually it's an angle of 60 degrees. We calculated it, and we want to know, what is this distance here? Okay, what distance did this boat travel? Okay, so we have a formula that says distance equals speed times time. So d equals s times t, which I'm trying to find out distance, right? Well, what is the speed at which the boat is traveling north? Which of these velocities would I want to use? Well, I probably want to use the river's velocity, right? 7 meters per second. So that is the speed I'm going to put in, is 7 meters per second times how long was the boat in the river, is another way to kind of look at it. How long was this boat in the river? Well, I believe it was 20 seconds, right? We figured that out in the previous problem. So what is 7 times 20? It is 140 meters, and that would be my distance. Okay, that would be how far down the river the boat traveled. That takes care of this video. I will see you guys next time.